3, 2, 1. Actually, let me put this shape on the screen. Let me change this with the gray. We'll change it to just floating above, and I can move it down. Turn that off. We'll make it be just as wide as the screen, and we'll make it float around. All right. Okay, so we're going to go over some of the questions from the assignment that I gave you last week. So let's do a couple of things first. Number one, if the majority have not done these problems, what I would like for you to do is go ahead and get the problems done. So the problems that I'm working on, or that I'm going to go over, it's number 19, and then we're going to look at number 22, and then number 38. So if those particular problems have not been done, I would like for you to pause the video, take some time to go over that, and maybe take 15 minutes at most and go through these problems. You can use the iPads, or if you have them printed off, do them that way. If you have done them, if the majority of people have done it and you just want to kind of watch through the video, you're more than welcome to just simply go through that. But it will be immensely more valuable to you if you have done the problems for yourself. If you have not, and you're just simply going to watch, you will not get as much out of the lesson. So I'll let you guys take that and do what you want to with it. Number 19, it starts off and it says, it's back to school again. It's based on the 74% national retention rate described in exercise 17. We did not do exactly 17, but we did an example where we had to write out the normal distribution, take the mean and standard deviation, and apply the 68, 95, 99.7 rule. So we did discuss that last week. So we're going to take that concept and kind of take it to the next level. And we're going to talk about probabilities in a situation like this. So it's based on 74%, which is the national average, the national retention rate described in another example. Does a college where 522 of the 603 freshmen returned the next year as sophomores have a right to brag that it has an unusually high retention rate? In other words, what we want to ask is, do they have bragging rights? More specifically, I guess in more of a probability or statistical question, it would sound like this. Is their average so much higher than the national average? Or more specifically, that it's that high due to something other than random chance, meaning they actually have a school that is much better on average than the national school. So they're different. They're not just getting lucky one year and getting a really high average. Is this average due to something that's statistically significant? So the information they give us is the probability is 0.74, so that's our P. X, number of successes, in this case would be the number of students that return back after their freshman year, meaning the retention rate. So you have 522 out of the 603 freshmen. If we look at some of the numbers, how we're going to do this, if we're going to, I've asked for probability, so really I'm asking you to look at normal CDF. And we've already established that it is normal. If you look back at number 17, it does go ahead. The problem is, do you think it's appropriate? And this, of course, is appropriate. And so we're going to need to calculate our standard deviation in order for us to use our normal CDF to get that probability done. So if you remember, our formula for for standard deviation looks like this. It's going to be the square root of P times Q divided by N. And so I plug that in for you. You should have gotten 0.018 to be my standard deviation. If we kind of take that idea and simply ask what is the question we're trying to answer. It says, what's the probability that the sample could be as high as 86.6% or about 87%. So you're looking at quite a bit of an increase in the percentages. The national average is 74. They're getting close to 87% for their average. And that's the question is that really high? And is that an unusual observation? What we've talked about in the past was if we had an observation that was over 2 standard deviations of the mean above or below, if it's outside that value, then it is actually an unusually high or an unusually low observation. So in this case, we have calculate the z-score. So it's 0.866 minus 0.74 divided by 0.018. This formula is the sample statistic. I guess in this case, we're looking at a proportion minus the mean divided by the standard deviation. Turns out that we get about 7 standard deviations above the mean, which is incredibly different than what we were expecting. 7 standard deviations above the mean. If we were to use normal CDF and to actually find the probability, it would be 0. There is almost no chance that we could get something this high if this was simply by luck. It would be so rare and so unusual for that to happen that we wouldn't ever expect it to. So, what does that all mean? Whenever you do a problem like this, you want to make sure that you actually answer the question. And so it says, because it's beyond 2 standard deviations above the mean, they do have bragging rights. This is something that's unusual, so it's not due to chance. It's due to the fact that they're different than the average school that they would be compared to. Okay. Number 22. In this case, it's going to ask us to go through a couple of things. It's information. This is number 22. Information on a packet of seed claims that the germination rate is 92%. What is the probability that more than 95% of the 160 seeds in the packet will germinate? Be sure to discuss your assumptions and check the conditions that support your model. So here we're kind of doing a full problem where it's asking us to check assumptions, conditions, and then to use normal CDF and calculate a probability for a sample of 160. So let's kind of take it through the assumptions and conditions. So at the bottom you can see randomization. If you think about the seeds that were in the packet, were they randomly selected to go into that packet? Well, probably not. They were probably simply thrown into the packet without consideration. But do you think that that packet of seeds is a good sample from the population? Do you think it would be pretty much like any other packet of 160 seeds? And so we would say yes. We are going to assume that this 160 seed packet is representative. In other words, it's not biased. Do I think that this particular seed packet is a bunch of bad seeds or particularly good seeds? I have no reason to think that it's any different than what would be in the population. And so whenever you write out your assumptions and your conditions, I do expect some sort of statement about each one, especially the randomization and independence. 10% and success and failure, those two things have to be actually calculated, and you'll see that in just a minute. Next part. In this case, we're trying to find probability, and so I didn't type this one out. I actually forgot. Do you think the 160 seeds would be independent of one another? So in other words, if I plant one seed, its result isn't going to affect the other seed's results. So we can definitely assume that they're independent. Here you have 10%. If I multiply that times 10, you get 1,600. And there's clearly more than 1,600 seeds in the population, so that's an easy one. Success or failure. Now this one is the one that says, well, can I use the normal probability? Can I use my normal CDF to actually find probability? If this fails, then I can't. I'm not allowed to use the normal CDF if I don't have a large enough sample. That's effectively what we're trying to show here. what the success and failure condition says that is if you multiply your sample size times the probability of success and the probability of failure, then we need to make sure that we have at least 10 successes and 10 failures. If I have both 10 or more, then we're okay. We're clear to use normal CDF to describe everything. In this case, we went through that, and it's obviously clear. One was close, but it was fine. So both are greater than 10, so therefore we can use the normal model to estimate. And here's where I plugged it in. Normal CDF, okay, in this case we were asking what would be the likelihood of 0.95. Let's see, that is... That's what it is. And so here you can see we can use the normal model, normal CDF. We're looking to go from 95% and higher. And so you have 0.95 to positive infinity with a mean of 0.92 and a standard deviation of 0.0215. Remember, standard deviation, this is still categorical data, so standard deviation we calculated would still be just like the one we calculated from above in this formula. Okay, and so those are two great examples, especially number 22. This is kind of when we have a quiz or test, when I ask you to do a probability question, I'm expecting this kind of scenario. I'm going to look for your independence and randomization, 10% success or failure. And then I'm going to look for a calculation of probability. Okay, let's look at some, this is notes, so this is actually kind of new. Quantitative data. I want to make sure that you have this down. So we haven't necessarily talked about this as much, but it's not really any different. There's one little tiny formula that we have to worry about, and that's bothering me. There we go. So quantitative data, the mean is going to be mu. They're going to tell you a mean, and that mean is going to be the mean of your sample. For standard deviation, they're going to tell you the population standard deviation. And just like before, we're going to have to calculate standard deviation. Except this time, they're actually going to mention standard deviation. If you remember, if you go back and look at any of the categorical questions we've talked about, there was never a mention of any kind of standard deviation. They gave you P, and they gave you sample size. If you look up at the top here, these are the things that they gave us. Never a mention of standard deviation. Well, that's different with quantitative data. They will give you sigma, which is our population standard deviation. And to calculate the standard deviation for my sample, X bar is the average. That's what represents, that's what your symbol is for your sample's standard deviation. We're going to divide the standard deviation of the population by the square root of our sample size. Okay, next thing. Assumptions and the conditions. These are going to be pretty much the same things. You're going to have randomness, independence, and 10%. And that's exactly as it was before. There is no difference in the way that you write it for quantitative or categorical. Number 4 is different. If we go back and look at these, success and failure requires you to multiply n times p, or n times q. And unfortunately, p and q represent success and failure. There's no such thing as a success or failure with quantitative data. Quantitative data, and number 38, the one we're going to look at in a minute, it's talking about average rainfall. So there is no such thing as a success. It's what was the average rainfall for this particular year or for that particular year. So you can't have a success or a failure. So we have to change it. And it still means the same thing. We're still trying to find a sample that's large enough. Just like before, we wanted to make sure that they were larger than or equal to 10. So it's still trying to find a large enough probability so that we can use a normal model. And here, we want to make sure that our sample is large enough so that the normal model applies. And so n would have to be greater than or equal to 30 as long as, and this isn't written on the screen, so make sure you write this down, as long as the normal model, or the population, is normal, you can have smaller sample sizes than 30. In fact, it doesn't matter how big the sample is. As long as they tell you the population is normal, then you can assume every sample from that population is also approximately normal. So when it is skewed, or it's not mentioned what the population shape is, or the fact that it's not normal, as long as we don't know that, then when you go to check this condition, large enough, we just simply call it sometimes large enough, but the large enough condition says that your sample size has to be greater than or equal to 30, and it's either it is or it isn't. So very easy to figure out. All right, number 38 is a lot more comprehensive problem, and it's a good one to look at. You'll probably have kind of a homework quiz kind of like this, so pay attention. Number 38 starts off and it says, I'll just read it to you. Statistics from Cornell's Northeast Regional Climate Center indicate that Ithaca, New York gets an average of 35.4 inches of rain per year, with a standard deviation of 4.2 inches. Assume that a normal model applies. Now, that's important. It says that we can assume that the normal model applies for this. And so I don't really have to check anything to start off with. I'm going to assume it's normal, so I can go right into using normal CDF. And that's kind of what they ask us to start with at first. During what percentage of years does Ithaca get more than 40 inches of rain? And so it's not really asking us to take a sample. It's asking for 1 year, which is fine. I can go right into that. I can look and I can actually calculate it. And so when we're only taking a sample of 1 rather than multiple samples, like with sample size of 5 or 10 or 40 or 50 or whatever, I would have to recalculate standard deviation. But in this case, it's a sample of 1, so we can go right into this. 40 to positive infinity would represent more than 40 inches of rain. The average is 35.4. If you calculate standard deviation, well, in this case we don't have to because they gave us 4.2 as my standard deviation. So it looks like about 13.7% of years have an average rainfall of 40 inches or greater. Okay, that one should be pretty straightforward. Part B says less than how much rain falls in the driest 20% of all years. And I drew a picture. Excuse me. And this is kind of what we're looking for. This is tricky. This is easy, but it's the way that the question is asked is kind of backwards, and you may not realize that. But pay attention. This is pretty straightforward to get once you see what we're asking for. It wants to know this x. Where is this x? What number breaks this into 20% at the bottom and 80% at the top? Okay, recognize that I'm not asking for probability, so that means I cannot use normal CDF. Right? If I was using normal CDF, it would be what is the probability of the following things. Okay, it's not asking. It says what is the number of inches of rain that marks off the bottom 20%. So in other words, it's asking for the 20th percentile. It's the same thing as on a standardized test. You could look up the test score that tells you the bottom 20% of the test scores, or the 20th percentile. So I have two methods of approach that I can take for this. I can use the z-score formula, which I've written for you here, or I can use my calculator, and I can use inverse norm. In my opinion, inverse norm is much easier. And so, yeah, these red lines are just bothering me. So we can use inverse norm to do this, and here's how we're going to do it. So make sure that you kind of pay attention and look at this, and I'll kind of type in. So the numbers that you put into inverse norm, we've done this before, but just to refresh your memory. So we're looking at the percentile goes here, and then your mean would follow with the standard deviation next. And so that's what we've typed into inverse norm. Now notice the percentile. And we've said this in the past, but the percentile you're looking for here has the bottom area, not the top area. So if I wanted to know the top 10%, then in this case over here, we would, instead of typing in 0.10 for 10%, we would have to type in 90% because it's about the area to the left, never the area to the right. So anyway, if we put this in there, it turns out it gives us 31.9, which makes sense. It's less than 35.4, and it's not that far off, so it makes sense. So if we were to get less than or equal to 39 or 31.9 inches of rain, then I know that I'm in the bottom 20% of years for rainfall. Part C, it says Cornell University student is in Ithaca for 4 years. So now we've increased it from one particular year to 4 years. And they want to let, it says Y bar, I chose X bar, to represent the mean amount of rainfall for those 4 years. So describe the sampling distribution model of this sample mean. So now we're taking a group of individuals, and we're going to create a sample of 4. And we're going to go through that. Because we've taken a sample size larger than 1, we have to check our assumptions and conditions. Randomization, so we would assume that all 4 years are representative of all the years. They're not anything special. Independence, this is obvious that the rainfalls are independent, meaning that 1 year's rainfall doesn't have an effect, doesn't cause the probability to change for the next year. 10% condition. Where there's more than 40 years of total rainfall, so obviously that my sample size isn't too big. Large enough condition, in this case we don't want it to be too small, so it needs to be large enough. The distribution is normal. Remember, it told us to begin with that we can assume the normal model applies to this group, so any sample size would be large enough in this case because the population is assumed to be normal. Now, it asks us to describe this, so whenever you describe a normal distribution, you want to talk about 3 things: shape, center, spread. And what we're going to do here is, since we went through these assumptions and conditions, we can talk about shape being normal. That's a lot more specific than just telling you it's bell-shaped and it's symmetric or single-peaked or something. We can say that it's normal with the standard deviation of 2.1. Notice it changed. This is the original standard deviation divided by the square root of my sample size, so divided by the square root of 4, or 2. And my mean would be 35.4. So I have shape here, I have spread with the standard deviation, and I have center with my mean of 35.4, which is the same mean as it was originally. Make sure you catch that. Now that we've established the scenario for the normal model, we know our standard deviation, we know our mean. Letter D says, what's the probability that those 4 years average less than 30 inches of rain? So now we want to figure out, okay, if we allow 4 years and we average those values, what would be the chance that on average the 4 years, that each year for those 4 years that you were there would have a substantially less amount of rainfall for those 4 consecutive years? And if we type that in, remember, it's the bottom percent, so we're looking at -1 E99 to 30. My standard deviation and my mean come from what we just did earlier. And this part right here, the standard deviation of x, which is sigma divided by the square root of n, this is the part that everyone is going to mess up on. Because apparently, like if we go back to the beginning, it simply asks for the probability that it happens for just 1 year. That's easy. And then I'm going to ask another question where it says, what about for 4 years? And you're like, isn't that the same question? No, because as you increase in sample size, we went from 1 to 4, standard deviation, or in this case, spread, shrinks. If you remember the penny example, we went from the pennies to the nickels to the dimes to the quarters. What happened each time? Spread got smaller. And that makes a very big difference when you're talking about probability. And so standard deviation changed. Make sure that when we talk about sample sizes greater than 1, you make sure that you do this part. Otherwise, it'll be wrong. Normal CDF of all that gives you a probability of 0.005. So it's actually very unlikely to see an average of 30 inches or less in 4 particular years. You would expect it to be a lot higher than that. A lot closer to the actual mean in case. Okay? And so I want you to try that. My goal is that you can be able to do a problem like number 38. That's kind of the ultimate goal for for this particular chapter. We didn't specifically talk about the central limit theorem, but it's really coming into play when you talk about the mean being the same and the standard deviation shrinking, and it's normal. So keep that in mind. Homework problems tonight. The pages will be uploaded on Classroom, so if you haven't already seen it, there'll be a new set of pages, of 2 pages for this. 37, 39, 43, and 48. Make sure you go through that. If there's a number of time left in class, I want you to take time and finish that up in class, or at least get started on it, talk with each other, and then we'll talk about this later. Probably going to be some kind of homework quiz, just to be safe. So if you have any questions, please email me. I'll be on email all day, and we'll pick up tomorrow where we left off today. Thank you.